Hello and welcome to this tutorial. I would like to introduce to you the several aspects of archaeometallurgy, which is an advanced natural science discipline connecting mineral resources, pyrometallurgy, and the production of archaeological metal objects. Archaeological sites related to metal production provide valuable information about the metallurgical processes, technical know-how, and materials used. Indications for metallurgical activities in the field can be slag heaps, mining traces, or workshops, or specialized areas in settlements. Findings related to ore processing can be grinding stones, punching mills, or tools. Indicative for the smelting process are technical ceramic finds, such as crucibles, wind nozzles or tuyers, furnace constructions, or furnace lining. Products of metallurgical activities can be found, such as slag, matte, spice, raw metal, or ingot lumps. Many field evidences have shown that the extraction of ore, crushing, and smelting took place close to the deposits and in distance from settlements, whereas the metal production to form objects usually were performed in workshops, often directly in towns. Questions arising when metallurgical activities are assumed are the reconstruction of the smelting process, technology, the ores and fluxes used, resource procurement, process parameters, and the metal that has been produced can be investigated. The provenance of the metals. Was there metal deposit in close vicinity? Have local deposits been used, or was metal rather imported? Was scrap metal recycled? The overall conclusions can be drawn concerning the economic situation, trade relations, or political structures. Has small-scale metallurgy been performed, or rather industrial production? Were metallurgical activities independent, or were governmental structures dominant? How extensive was export and import of ores or metals? Who were the trading partners and which trade flows were followed? Diagnostic findings and finds of different material groups contribute to the overall picture, and the more material can be excavated, the better conclusions can be drawn. Sturm developed a model after which the different stages of metallurgical activity in copper metallurgy had developed over time. In the preliminary phase, no pyrometallurgy is involved, but the first exploitation and use of metal-containing minerals can be detected. Colorful minerals from surface enrichments are used, for instance, as pigment for painting. The initial phase introduces the first melting of copper, supposedly using native copper. Innovation and experimental phase is initiated by the first smelting of oxidic copper minerals in crucibles, which comes along with first production of crucibles, petards, controlled smelting environment, and possibly metal globes as relics from the pyrometallurgical smelting in the soil. Consolidation phase follows with advanced smelting of sulfide minerals, and furnaces, furnace slags, and slag heaps occur. Last stage is the industrial phase, which extends smelting activities to industrial scale, which are accompanied by the advanced mining technology, large furnaces or furnace installations in plants, huge slag heaps, settlements for the miners, and infrastructures. The cycle of copper production and working follows the theory that material cannot be consumed but will remain on Earth. The right half of the cycle stands for the technical activities. The resource in the natural world at 12 o'clock undergoes the mining, ore processing, and smelting at 3 o'clock, then followed by production of the finished artifact at 6 o'clock. The left half of the cycle concerns the social aspect of artifact use and waste, and finally the circle closes with archaeological contribution of excavating and collecting in the museum. I will concentrate in the following on the right half of the metal cycle. I skip here the mining of the ore and spend some time with the processing and smelting techniques. Both oxide and sulfide ore needs to be crushed and washed to separate the heavier ore from the waste rock. Documents and field evidence can help to quantify the technological standard of ore processing in the different places, regions, and periods. Evidences of the innovation and experimental phase concerns the smelting of oxide ore. Crucible finds stained with copper residue point to crucible smelting. Bowl furnaces were dug into the ground, and this construction already allowed that air is actively blown into the fire. Charcoal is needed to maintain a reducing fire, which is required to gain metal from the smelting process. The consolidation phase goes along with shaft furnace constructions and the smelting of sulfide ores. These furnaces had a comfortable height, as this example of experiments show. They were in use from the Bronze Age on and then continuously for quite a long time. From the consolidation phase on, sulfide ore could be smelted, which in contrary to the smelting of oxide ores, required pre-roasting of the ore to convert the sulfides into oxides. The roasting bed is above an open fire for best exposure to oxygen. The sulfur is removed as sulfur dioxide fumes. In medieval up to modern times, large installations for the roasting process were built in plants, demonstrating the huge dimensions of metal smelting and of course also the tremendous pollution. Roman and medieval pollution from metal smelting is still today detectable in Arctic ice cores and also in sea sediments. After roasting the sulfide ore and converting it to oxide ore, the roasted material became much softer and easier to crush. It was crushed first by hand, as can be explored in experimental work, or later in large crushing mills. The crushed ore, which is roasted, is then smelted under reducing atmosphere in either crucibles in a pit fire or larger quantities in furnaces. Note that the reducing atmosphere is crucial to produce the metal. During the reductive smelting, different materials form, and these stratify due to the gravity separation. The heavy metal sinks to bottom, the slag floats up, copper matte forms between the metal and the slag. The gases escape if not prevented by closing with a lid. Intensively studied were the shaft furnaces of the 12th and 10th century BCE, found in excavations in the Wadi Araba. Mining of copper ores and smelting activities took place here from Bronze Age until modern times in the different stages. Usually, this is all what is left from the furnaces in the excavation. Layered structures indicate here that these furnaces were built up again many times and allowed their reuse. This is an example from Fenan. Timna in Israel and Fenan in Jordan are geologically related and represent huge copper deposits. Here, several furnaces were built in a row, representing an industrial dimension. This way, the furnaces could be kept running continuously. The copper production was increased significantly this way. Industrial-scale high shaft furnaces were not limited to copper smelting. but were also identified for silver smelting. The reconstruction is what you can see here is one of the most prominent examples, the silver smelting site of Lavrion in Greece. Medieval smelting reached a perfection. Many hands were necessary to run industrial metal production. Successful smelting is depending crucially on controlled and sufficiently high temperatures in the furnace. Natural wind resources can be employed, but in most cases, manpower is necessary to blow wind into the pits of furnaces. The employment of natural wind is known from archaeological evidences and also from ethnological studies. Wind furnaces are built on exposed places. These furnaces were potentially only seasonally used on windy days or on windy months. Here are examples from South America, here from Bolivia. More controllable are alternatives based on human power. Besides blowpipes, bellows are highly effective. Different bellow types work. Single bellows and back bellows are operated by hand. If operated by 2 or more people at a time, very rhythmic and synchronous moves are necessary to keep the temperature on fire. Pot bellows are operated with the feet moving up and down. See a Chinese artifact on the left, an Egyptian drawing in the middle, and reconstructions of such pots in experiments from 1990. Box bellows require more muscle power. As seen in the drawings of a Japanese example, they are constructed a way that they can be operated by 2 men. Tuyers are the crucial part of bellow blowing. They are made of tempered clay and protect the tip of the blowpipe or bellow from burning. Tuyers were found in many smelting contexts, such in the Levant or in Egypt. Smelting experiments can make visible the heat affecting the ceramic. The very ends are slagged or glazed by reaction of the clay. Efficiency of bellows can be investigated by experimental work, as has been developed in a master thesis in 2019. Slagology is not an official term, but it is a research field on its own because slags occur in a great variety and with distinct chemical and physical properties. Also, their microstructures, their inclusions, and other components can help reconstructing the smelting process in very detail. Mineralogical and chemical studies of slags are useful for the reconstruction of ancient smelting processes. Process parameters can be reconstructed by the slags, such as the smelting temperature, the oxygen supply and the atmosphere in the furnace, the composition of the ore, the mixture of the flux, and the metal yield. Methods for the analysis of slags applied are XRF, XRD, SEM, EMPA, ICP-AAS, ICP-MS, and of course, polarized light microscopy on thin sections. Also, modern experimental metallurgy can add valuable insights into the properties of the slags, such as the relation between viscosity, elemental composition, and smelting temperature. The 2 images show that the surface shape of slags highly depend on their viscosity. Crystallized phases, metal inclusions, shape and size of the crystals, their phase composition, glassy component, and the texture can be linked with phase diagrams in order to explain the ores used, the processes, and the smelting components. Some constituents can be indicative for the perfection or the failure of the process. Classification of the slag can help to understand the great variety of slag compositions. This is a scheme developed in his dissertation in 2016. The products yielded in smelting experiments can be compared with archaeological examples. The presence of entrapped charcoal, for instance, can explain different temperature zones influencing the crystallization of phases in a slag. In order to trace the ores that have been used for the production of objects, different analysis methods are used. First, elemental composition is compared in original ore and the objects. In this example from Fenan in Jordan, copper ingots were compared with ores. Fingerprinting the ores in archaeological objects is made possible by lead isotope analysis. The ores have significant isotope pattern, which is related to the geology of the ores. This pattern does not change during the smelting procedure, so that it is still preserved in the object. Analyzing the object can hence trace the ore deposits. Other isotope systems are also used in archaeometallurgy. They can supplement a picture that is drawn with lead isotopes. This diagram is from smelting experiments. All agents were analyzed separately, comparing ore, roasted ore, fluxes, fuel, intermediate products, and metal yield. It was the aim of the experiments to prove that the copper isotopes do not substantially fractionate during smelting. This is a prerequisite for provenancing of ores in objects by isotope analysis. I would like to close this tutorial with one last challenging take-home question. It links quite unusually metallurgy with the production of glazes on ceramic. By accident, furnace lining or bricks used for the copper smelting furnace can be slagged by the high temperatures. When copper vapor is at the same time present in the furnace, blue, green, red, or black glazes can be developed, similar to the glazing of ceramic. So what came first, glazing technique or rather copper metallurgy? A brief reading recommendation should encourage you to dive into the subject even deeper. So if you are interested to learn more about archaeometallurgy, check the literature. There is way more available than this list. Enjoy the work in archaeometallurgy.